Now we're going to use MO theory to understand something called hyperconjugation and carbocation rearrangements. So we're going to use hyperconjugation to explain trends in carbocation and alkene stability. We're going to, before we explain them, just describe the trends. And want to predict the relative stabilities of carbocations and alkene isomers. We're going to want to, and then we're going to switch gears, talk about something called carbocation rearrangement, propose curved arrow mechanisms for carbocation formation and rearrangement, and then try to predict whether or not a given carbocation will rearrange. Okay, hyperconjugation. This, we don't even know what it means, but I can tell you now, it's going to feel like a misnomer. You're all biologists. Hyper usually means more, right? In this context, it's going to mean like kinda conjugation. Of course, we don't even know what conjugation is, so hey, let's get started. So the relative stability of carbocations exhibits the following trend, and I would like for you to consider how you can describe this trend. Well, we can see that this is the least stable cation, and this one is the most stable. That means that this is the highest energy. Okay, so if we had an energy axis, this would be the highest energy, and this would be the lowest energy. So while I've been rambling, hopefully you can see what's happening is that these H's are being replaced by alkyl groups. So what we can see here is more alkyl groups on the carbon with the positive charge. So this is a carbon with an unfilled octet. It's electron poor. It only has 6 electrons around it. The more alkyl groups on the carbocation carbon, the more stable the cation is. So that's how we can describe this trend, okay? Of course, we want to understand it. Before we move on, I want to introduce some terms. It says substitution pattern here. Substitution pattern refers to the number of alkyl groups bonded to some atom, and it really varies from functional group to functional group, which atom you'll be referring to when you think about its substitution pattern. For carbocations, which is what we have here, we have carbocations. We want to look at that carbon with a positive charge. And so this first one, it has no alkyl groups, just hydrogen. So this is the methyl cation. It was the least stable. And the second one, can be described as a primary cation. There's one alkyl substituent, that one, on the carbon that bears the positive charge. Then we have a secondary cation because there are 2 alkyl substituents, and that's a little bit more stable. And then finally, in this group, the tertiary cation is the most stable, and it's called a tertiary because it has, you guessed it, 3 alkyl groups on the carbocation carbon. Okay, so more substitution, more stable. That's another way to describe this trend. So we can describe the trend now. We would really like to be able to explain it. And this can be explained by the funny word, hyperconjugation. Okay, cool. What is hyperconjugation? Well, let's think about what the stress is on these molecules. So the stress is that the carbon is electron poor. It has an unfilled octet. So how does this molecule stabilize that stress? Well, it's stabilized by electron donating alkyl groups. Now you might wonder, well, how does an alkyl group donate electrons? Well, I will show you. So let's go ahead and draw the carbocation carbon, and I will go ahead and I'll draw the primary cation. So we have this empty p orbital on carbon. And we have learned that empty orbitals can overlap with filled orbitals, and that will stabilize electrons. Okay, so here's our p orbital on carbon. It's empty. If it could just overlap with some filled orbital, the electrons in that filled orbital, well, they would be stabilized, right? They would be stabilized. And not only would they be stabilized, the charge would be shared, and that's good too. Okay, so what filled orbital can they overlap with? Well, it turns out they can overlap with a sigma CH or a sigma CC. So I'm just going to draw a sigma CH orbital. It's filled. And it is similar size and shape to the p orbital. And at this moment, it's occupying the same plane as the p orbital, so it's kind of aligned. It's not perfect. I guess we could be more precise. Would you like to say partially aligned? It's, not parallel at all, but they're sort of aligned. And so they can overlap a little bit. So you're going to have a little bit of overlap, a little bit of sharing between those two orbitals. And so that not only shares the charge, which is really, really hard to show, but it also relieves some of this electron poor nature of carbon because you're sharing these two electrons with it. It shares the charge, and it ultimately stabilizes the electrons in the sigma CH, or this works with a sigma CC bond as well. And so I showed this with a primary cation. And of course, this interaction, this is momentary because, there's free rotation around this bond. But in another moment, maybe one of the other hydrogen bonds will be aligned with the CH bonds will be aligned with the p orbital, and that one will overlap. So the more alkyl groups that you have, the more of these hyperconjugation interactions that the molecule has. So the more hyperconjugation, that means more sharing, and in general, that's going to have a lower energy of the electrons, and the charge is also spread out, and that's really stabilizing as well.
Hyperconjugation is the overlap of a sigma CH or a sigma CC orbital, that filled orbital, with an empty orbital of pi symmetry. There's a node for the orbital on the internuclear axis. That's what I mean by pi symmetry. So these two orbitals, they're sharing electrons. The sigma CH or sigma CC, it's donating electrons into that empty p orbital. So that interaction is hyperconjugation. It explains the observation that electron groups are alkyl groups, are electron donating. And it explains why the more alkyl groups on a carbocation carbon, the more stable it is, because all three of these are donating electrons by hyperconjugation to that electron poor carbon. Now let's look at some more examples of carbocations. So here are two carbocations, and I want you to consider their stabilities. And specifically, I want to know, are they more or less stable than the tert-butyl cation? So this was that tertiary cation that was maximally stabilized by hyperconjugation on the previous slide. So are these, we'll call them A and B, are they more or less stable than the tert-butyl cation? Well, let's think about what factors there are for them. So hopefully for A, you recognize you have a lone pair adjacent to an empty orbital. And then if you didn't recognize that, now that I've pointed it out, what do you know we can draw? Yes, we can draw a resonance structure. Okay, so this resonance structure describes that carbocation. In fact, it even has a fancy name. It's called an oxocarbenium ion. Ooh, very fancy. Okay, and this resonance structure, this is actually even the major resonance structure because all the atoms have filled octets. I know it gets tough because you see the formal charges on oxygen, which is more electronegative than carbon, but octets are the most important factor in determining what the most stable resonance structure is. Okay, so A can be described by a resonance structure. Let's take a look at B. Hopefully you've seen the theme. And so for B, we have a pi bond adjacent to an empty orbital. And this is another one of our patterns for recognizing resonance structure. So we can show resonance structure here. Okay, so both of these molecules, there are resonance structures. Now, both of these molecules are stabilized by what's called conjugation. There is a direct connection between, for the oxocarbenium ion A, this lone pair is actually just shared as a pi bond. And, both resonance structures describe the molecule, but one of them has just full sharing as a pi bond. Whereas for B, sorry about that, we have sharing of these pi electrons in a resonance structure as well. So A and B, they have conjugation, direct connection. They have actually what's called an extended pi system, or they have pi systems. Let's not get too complicated here. Pi systems or pi bonds that spread out electrons and charge in this case. And that was not the case here. There were no pi bonds. We did not draw any pi bonds, right? We just had some kind of sharing when this orbital is aligned, which of course it only is sometimes because there's free rotation around the single bond. So this was hyper. So it was a little bit of connection, a little bit of sharing. I know it feels weird. Hyper here means little connection, a little bit of sharing. Whereas conjugation is just full direct connection. You have pi electrons spread out, sharing of electrons, full sharing of electrons and charge. Oh, so we didn't even finish. So then, do we think that each of these is more or less stable than the tert-butyl cation? Each one is more stable. Okay, so each one is more stable than the tert-butyl cation. So now I'd like for you to pause and try to define hyperconjugation and conjugation, and then think about this question again.
So conjugation involves connected p orbitals, and they can be described by resonance structures. So there's full sharing of these electrons all the time. This molecule is described by both of these pictures. It's some composite. Each of these atoms has a p orbital, and we'll talk more about these types of systems and organic chemistry too. Versus hyperconjugation, which really means like a little bit of connection sometimes. And this is the overlap of a sigma CH or a sigma CC filled orbital with an empty p orbital or pi orbital. So here you can see for the carbocations, sigma CC is aligned with a p orbital. And when they're aligned, there's some overlap, but there's free rotation around this bond. And so it's suddenly not aligned, and so there's no overlap, and it's just a temporary thing. It's not like this full sharing of electrons that we have in conjugation. And so because of that, conjugation is a stronger effect, it's a more important effect than hyperconjugation. So it just means that cations with resonance structures are typically, and not always, but typically, more stable than without resonance structures. Okay? Typically, not always. Okay, so we're going to move on and we're going to think about alkene isomers. So we've used hyperconjugation to explain why tertiary cations are more stable than secondary, or more stable than primary, or more stable than methyl. And then we compare that to full conjugation, which we said was a more important effect. And so now we're going to just shift gears and not talk about carbocations for a moment, but talk about alkene isomers. So there are two structural factors that affect the stability of alkenes, and we're going to state those trends that are related to each of the following factors. So first, substitution again. So let's talk about that. So we have an alkene. There are two carbons of an alkene, and so there are four different A, B, D, and E, four different positions where you might have substitution. So if you have no substitution at any of those positions, then you would have ethylene. If you have substitution at one of those positions, so you have an alkyl group instead of a hydrogen, then you would have what's called a mono-substituted alkene. You can imagine having substitution in two of those positions. It could look like that. It could look like this. It could look like this. Okay, so having substitution at two of these positions, this would be called disubstituted. You could have trisubstituted, or three of A, B, D, and E are alkyl groups. And then finally, you can have tetrasubstituted. So the most stable is the tetrasubstituted. The most stable. So that's, well, we'll stay with this. So that's the lowest energy. Then tri, then di, then mono, and then ethylene. So let's just write that out. So we would have the most stable for tetrasubstituted, which means lowest energy. And then for the unsubstituted, or the monosubstituted, these are the least stable alkenes. Cool. So substitution pattern, and then also stereoisomers. So when we look at the disubstituted, the trans is actually more stable than the cis. So the trans is the more stable isomer. So we have two factors that are going to affect alkene stability: substitution and then which stereoisomer you have. Now that we can state those trends, we want to understand them. So we want to understand why the trans alkenes are more stable than the cis. I've taken the trans and cis isomers and I've just rotated them. I flipped them in space by 90 degrees, and this is so we can get a good look at the pi orbitals. So for the trans, which is more stable than the cis, we can see that those R groups are pointing off into space in opposite directions. So this one's coming out at us, this one's going back into the page. If you can't visualize that, even if you can, I encourage you to get your model kit out and check out cis and trans alkenes. I'm not up for being on camera again today, but you should get your model kits out and try. Now for the cis alkene, I rotated that in space by 90 degrees, and then for this one, the R groups are coming both out at us. And even if you make methyl groups, you'll see that those groups are clashing in space. Their electron clouds are overlapping. This is called a steric clash. And this will occur anytime those groups are coplanar. And of course, if the two R groups try to move in space to not be coplanar, then that's going to disrupt the pi bond because you have to have these p orbitals aligned in order to have a full pi bond. So that steric clash where the molecule is penalized either by the R groups overlapping in space, or if it rotates to deal with that, then the pi bond isn't a full over interaction anymore. That causes this isomer to be higher energy or less stable than the trans isomer. Okay, so I think that this we can understand, especially if we think about it one more time if we need to. A little bit more difficult to understand might be the relationship between substitution pattern and alkene. So we saw that the more substituted an alkene is, the more stable it is. So the tetrasubstituted alkene was the most stable. And we need to understand why. Well, it says use clearly drawn cartoon molecular orbitals in your explanation. And that means you're going to need a filled orbital and an empty orbital because those are the ones that productively overlap. This is a pretty hard one to figure out on your own. So I will tell you the empty orbital is actually pi star. So this is pi star Cc. And then I'm going to just use probably the mono substituted because I'm too lazy to draw too many things here. So here's a mono substituted. Okay, we'll just make it a methyl group on that mono substituted alkene. So one of the sigma CH bonds in that mono substituted alkene for that's a methyl group, but it could be a sigma CC as well. It is aligned with pi star, and so there's a little bit of overlap here. Now, of course, there is free rotation around the sigma CC bond. Okay, so there's free rotation around the sigma CC bond, and this will be out of the plane in just a second, and then this one will be aligned, and it will overlap, and then this one. And then the more alkyl groups you have, so you have disubstituted, or you have trisubstituted, or you have tetrasubstituted, the more alkyl groups you have, the more of these interactions you have. And so there's more overlap, there's more stabilization of electrons, and so you have more stable alkenes. Now, I find hyperconjugation in alkenes a little bit harder to understand because you're not stabilizing charge. You are just sharing electrons. And, when I put up that slide, like chemistry is all about electrons, we often list sharing electrons lowers their energy. And that's what's happening here. Okay, so we're done with hyperconjugation. So review this, be able to draw the interactions, be able to state the trends. We'll review all the learning goals at the end. So now we're going to go back to talking about carbocations. And I want to introduce to you a way that carbocations can behave, which is called rearrangement. And I'll just say from the outset, not all carbocations do this. Not all cations are going to rearrange. So we'll talk about when they do and what that is and all of that now. Okay, so speaking of this slide, so chemistry is all about electrons, and electrons are most stable in the lowest energy orbitals. And so we saw for hyperconjugation, even though it was really weird, even though we had a sigma CH really low energy electrons, they were overlapping with a p orbital if it was empty, or they were overlapping with pi star. And they did that because you still formed two new orbitals. And even if you just stabilize electrons a little bit, that was good, that was favorable. You went to lower energy here. So think about based on what you've learned so far, what are the lowest energy places for an electron? And I'm going to skip it this time. That's for you to try. Now we're going to rebrand this statement. So high energy species are unstable. And why is that? Well, that's because the electrons are high energy, right? They're in higher energy orbitals. And then high energy species, they're going to react to achieve lower energy. So before you move on, I want you to predict how this might apply to carbocations. And I'm not answering this question right now. I really need you. I'm serious. For reals. Pause and consider how this statement might apply to carbocations. So carbocations, how are they formed? Well, they can be formed in different ways. And one of those is by heterolysis of a CX bond. So heterolysis is one of those elementary steps that I've asked you to learn. And it's just simply bond breaking. That's all it is. So carbocations can be formed by heterolysis of a CX bond. I want you to take all of these alkyl halides that I have listed here, break the CX bonds, draw the carbocations, and then label the electron poor carbon with its substitution pattern. So methyl, primary, secondary, tertiary, whatever that may be. Please try this on your own. Okay, here's your answer. So what we have happening is the CX bond cleaves. The electrons go with the halogen, and I haven't shown the halides here because I don't care right now about that. I really only care about the carbocations. So we have these carbocations. There are 6 electrons around the carbon. They don't have filled octets. And so that's the same for each of these species. Okay, so just these are sp2 carbons. Let's just draw one of these. I'm going to draw this one over here. And just really want to point out to you, this is an sp2 carbon, and it has an empty p orbital. And we've talked about that. I showed you how it's stabilized by hyperconjugation. Okay. All right, and that's definitely the stress on this molecule, that the charge, the electron poor nature of that carbon, that's a big stress on these molecules. I asked you to label the substitution pattern, and that's because we know substitution pattern determines stability of carbocations. So these are all secondary carbocations. So can we recall what the most stable carbocation is as far as substitution pattern? Yes, the least stable is going to be methyl, and then primary, and then secondary, and then tertiary, and then even more stable than that would be resonance stabilized or delocalized charge. So, I mean conjugation. Okay, so for example, the allyl cation, this cation, that you can draw resonance structures to describe. So we're at secondary, so we're here, so we're not the highest energy, not the lowest energy, but, pretty high energy. So it turns out that each of these carbocations does something called rearrange. And I've shown you what they rearrange to. And I really want you to, again, there's a lot of pausing in this little exercise, but I want you to pause and draw the curved arrows, describe the orbitals involved in the rearrangements, and try to explain why each carbocation rearranges. And you have a big clue. Your clue is here and here. Okay? So I want you to go ahead and pause, and please try this question on your own. So a place to start with this answer is that each of these rearrangements occurs because the cation that it forms, so each of these cations, it's lower energy than where you started. So in each case, it's going to be downhill. So I've given an example for actually the last one. I drew an energy diagram. And from the secondary, so the tertiary cation, you've gone to lower energy. Cations are really high energy intermediates. And so they react to alleviate that energy, even in this really weird way. Okay, but we're going to go step by step. Now look at each of these examples. And in a way, I have done the hardest example first. So what we have happening here is we have a secondary cation. Okay, so we have a secondary cation. And this secondary cation clearly is undergoing a rearrangement. It's gone from a 4-membered ring to a 5-membered ring. I've color-coded the carbons so you could number them. And the electrons in this bond, sigma CC, they've moved over and they've made a bond with the pink carbon. So the blue carbon no longer bonds to the peach carbon. It bonds, doesn't belong to anybody, but it bonds to the pink carbon. And when it does that, you end up with an unfilled octet on the peach carbon. And so this is your carbocation carbon. Now this one is a little bit weird because you go from secondary to secondary, and so I probably shouldn't have started with this, but it relieves the ring strain. So even though the substitution pattern of the cation is the same, this has still gone downhill to lower energy because the ring strain is relieved. So that's why this first rearrangement happens. Spend some time with it. It's hard, but I've color-coded it for you, and I've drawn in the implied hydrogens, and I know you can do it. So for the second example, we have this secondary carbon, the secondary carbocation. So there's an implied hydrogen here, and it is still here in the product. And it's adjacent to this quaternary carbon. So quaternary carbon has 1, 2, 3, 4 alkyl groups bonded to it. And if that methyl shifts over, that's what I'm showing here. So sigma C electrons go to the empty p orbital. It's called a methyl shift. If that happens, then what you see is formation of a tertiary cation. And tertiary cations are lower energy or more stable than secondary. And so that explains why this rearrangement takes place. And then finally, for the third example, we have a secondary cation adjacent this time to a tertiary carbon. And so this time, that we see a hydride shift. We see this hydrogen moving with its electrons. So sigma CH to the empty p orbital on carbon. And the reason that the hydride moves, you should just think about it like in physics. It's small. It's not very massive, so it's easiest to move. It has the least inertia. I've probably misused one of those terms, but the least massive thing is going to move typically. So we see this hydride shift here, and this forms a tertiary cation, which is lower energy than the secondary. And I demonstrated that with the reaction coordinate diagram up here. And so that's why this rearrangement occurs. Okay, everyone needs to chill. We're not going to lose our mind over carbocation rearrangements. We are all going to chill. And I say that in the kindest way possible. Not all carbocations rearrange. Rearrangements only occur when a more stable carbocation results. But it's confusing, so we're going to talk about it now when we're kind of focused on it, and then when it happens to us later, we won't be surprised. So it only is going to occur when it generates a more stable cation, like in this case, secondary to tertiary, or some ring strain is relieved. Okay, so each of these examples represents a pattern we can look for when we're predicting carbocation rearrangements. So if you would like to try to state that pattern yourself before moving on, I would recommend that. And I'm going to count to 3, so pause if you want and then go on to the next slide. Okay, so the first pattern that we have here is this 4-membered ring adjacent to a cation. And in this case, we can have this ring opening, and that relieves the ring strain. Next pattern, we're going to have a secondary carbocation. Remember, that was our intermediate stability, right? Those are the problematic ones, the intermediate stability. So a secondary carbocation adjacent to a quaternary carbon. And so in this case, we're going to have an alkyl shift. This was a methyl shift. One of those methyl groups moves over, and then now we end up with a tertiary, lower energy intermediate. So it's tertiary cation. All right, last pattern. When we have a secondary cation, again, the intermediate energy adjacent to a tertiary carbon, this time we can have a hydride shift. Okay. And then we end up with, I stopped labeling for some reason, a tertiary cation which is lower energy than its secondary counterpart. Excellent. So those are three patterns that we might observe. Are there any other types of carbocations that might rearrange? What do you all think? Yes. So, we saw they can rearrange to relieve ring strain. We saw they can rearrange to go from secondary to tertiary, so to have a more hyperconjugation stabilizing the cation. And then did we talk about any other factors that affected carbocation stability? Yeah, so they can rearrange to form a conjugated cation, or one for which you can draw resonance structures for. All right, well, spoiler alert, I have an example of that on the next page. All right, so we're not going to lose our mind over this. We're going to be calm. We're going to look for patterns. And yeah, we're just going to stay super chill because chemistry is fun. So pause and predict whether or not each of these carbocations will rearrange, and please explain your reasoning. All right, let's take a look. So this first one is a tertiary cation. The only reason this might rearrange would be to relieve ring strain, or if rearranging would cause it to be conjugated and have resonance structures, but those are not options. So that's a no for this one. Next one. Now, don't get excited. We have a ring. It's adjacent to the cation, but we're not going to have this ring popping open. Five-membered rings don't have any ring strain or very little ring strain. So that's not going to be a consideration here. But we do have a secondary cation, and we know that they are in those intermediate stabilities. So look at the carbons adjacent to it. This is the primary carbon, and if there's any sort of hydride shift, it's going to make a primary cation. Not going to happen. But its neighbor on the other side, this is a tertiary cation. Excuse me, tertiary carbon. Not a cation yet, but it can certainly rearrange. Make this hydrogen orange. And when it does rearrange, it forms a tertiary cation now. And tertiary is lower energy than secondary. So yes, we're going to have a hydride shift from the carbon that is tertiary. Okay, we'll delete that. Let's move down here. Well, we're on a roll with our secondary cations. So we have a secondary cation. It is adjacent to a primary carbon. That's useless, but also to a quaternary carbon. So this one, not so useless. We can have one of these alkyl groups shift over, and that will form, ooh, fancy. Okay, there's the methyl that moved. And then there was a hydrogen here, that's still there. Okay. And then we have a tertiary cation. And tertiary is more stable than secondary. So yes, we're going to have a methyl shift to form a more stable carbocation. And then while I'm writing all this, I want you to answer the last question. What do you think? It's secondary, adjacent to a secondary and a primary. So useless, right? Wrong. So this is really hard, by the way. But this secondary carbon is adjacent to this ring with all those pi bonds. So actually check out what can happen here. Okay, so this is what I was talking about. If you were like, what is she talking about? Haha, you're about to see. So we can have one of these hydrides shift, and that will generate this cation, so we went from secondary, and it's still going to be secondary, but now we can draw resonance structures to show how the charge is shared. And I can draw a couple more resonance structures, but I'm not going to do it right now because this is supposed to be a short video. But so this is going to be lower energy because it's delocalized. So delocalized, conjugated, can draw resonance structures, all different ways of saying basically the same thing. So this cation is lower energy. Can you guys hear my kids screaming right now? Super. All right, got it? So you might have to watch this again, think about these examples again, but you can do it. Summarize and reflect. This is all like very related to our previous classroom discussions, and it's important that you think about how. And if you have any questions, I encourage you to email me. Can you describe trends in carbocation and alkene stability? Yes, you can. More substituted is more stable. You just need to understand what it means to be more substituted. Explain trends using FMO theory. Yes, this is hyperconjugation. You should be able to explain it for the carbocations and for the alkenes. Predict the relative stabilities of carbocations and alkene isomers. Yep, more substituted is more stable. So you need to first stop and ID the substitution pattern. So if you see some carbocations, you need to stop and say, hey, that's secondary, and then think about what that means. Propose curved arrow mechanisms for carbocation formation and rearrangement. Yes, with some practice you can do this. And then predict whether or not a carbocation will rearrange. Remember, we are looking for patterns. I do not want you to be invoking carbocation rearrangements everywhere. Be chill. Look for the patterns. Look for these patterns. You can do it. All right, time to go practice.